So after going over sections 11.1, 11.2, and 11.3, we went over sequences, we went over series, namely geometric series and telescoping series. And so those series, when they converge, you can actually find their sums. And then in 8.3, we went over the integral test, which compares a series with an integral as long as the function is continuous, positive, and decreasing. If the integral converges, so does the series. If the integral diverges, so does the series. The only problem is we couldn't find the value of the series in this case. Okay, and next, what if we couldn't integrate? Well, it's not something we can integrate easily. So there's two tests that we're going to go over in 11.4. They're called the comparison tests. There is the direct comparison test and the limit comparison test. So we'll study these tests for a series of positive terms. Again, just like before, we have to have positive terms, and they will expand our library of tests for convergence of series. And the idea for these two tests is to compare the series that we're trying to find convergence for with a known series whose convergence or divergence is known. That's the idea, okay? And how to do that? Let's see. So first, let's talk about the direct comparison test. Direct comparison test. Put that on silent, okay. Okay, so let the series that we're trying to find the convergence of from 1 to infinity be a series with no negative terms. So all the terms in that series have to be positive or zero. Then that series converges if we can find a convergent series, if there is a convergent series sigma bn from 1 to n to infinity with every term in an is less or equal to every term, except for a few terms, for all n greater than some positive number n. If it doesn't work for the first few terms, that's fine, but as long as it's consistent after a specific term, okay? So the term the series whose convergence is sought, each term, after a certain number, has to be less than the term corresponding to the series whose convergence is known, okay? Also, we can talk about divergence. Sum of an diverges if there is a divergent series sigma cn of, again, non-negative terms, just like bn, like an, where an is greater or equal to be divergent, for this to be divergent, this to be divergent, for all, again, n greater than n. And the proof, I put it in the notes if you're interested in the proof, so I'll let you go over the proof. But let's look at applications for that. So test for convergence. Sum n times sine of 1 over n. N equals 1 to infinity. Remember, we used to do the integral test. So if I want to do integral from 1 to infinity of x sine 1 over x, this can be done. It's not easy though. You can try, I don't know, you can try integration by parts. It might not even work, integration by parts. So you can try that. So integral test is not going to work. So we're going to do what we call direct comparison test. But you know what would on this one? Let's call this first method. something we did before, the nth term test for divergence. If the limit as n goes to infinity of n sine 1 over n is not 0, then we know it diverges. Okay, we know it. Well, let's see. This is, we can write it as sine of u over u, like 1 over n over 1 over n. So this is u, and this is u, sine u over, if n goes to infinity, 1 over n goes to 0, so this equals 1. As long as it's not 0, then we say the series diverges. And that diverges by the nth term test for divergence. When we talk about strategy for conversion of the series, that's the first thing we want to try because it's the easiest one, and the strategy will come later. Okay, we're gonna group it all together. Well, the second method that we could do, which is the direct comparison test, is we want to compare this with a series which either converges or diverges. Obviously, we want it to be divergent. We know it's divergent. So instead of saying, if I knew it was convergent, I would say sine 1 over n is less or equal to 1. But we know it's also greater. We want it to be greater or equal to be divergent. So that's what we're going to do. And if we times it n is positive, so it's not going to change that. It's greater or equal negative n. So n. So if we do and since sum of n or negative n diverges, you can easily see that, right? There, the nth term test says it diverges. That means sum of n sine 1 over n diverges as well by the direct comparison test. By the direct comparison test. Okay. This is true for all n greater or equal to 1. Okay. Here's another example. Now, to do the comparison tests, you want to compare the one that you're finding convergence of with something similar. So something similar to this would be 1 over root n if you ignore the constant. So compare it with 1 over root n. So we start with root n minus 1. It's definitely less or equal to root n, right? Okay, but if we do 1 over, that's going to be greater or equal to 1 over root n, right? And this is true for all n. Now at 1, it's gonna be true, but we're starting at 2, so we'll just use 2. Okay. And you can see why we don't start at 1, because that would be undefined. For all n is greater or equal to 2. So since this is our an and this is cn, and since sum of 1 over square root of n equals 1 to infinity, that's n to the 1/2. It's a p series with p is less than 1, which diverges. That means our series diverges as well by the direct comparison test.